Okay, good evening, everybody, and welcome to this IMechE talk on Exovent. We're going to give it about another 2 minutes just to allow people who haven't quite joined yet or who may be struggling with the IT to join. So we'll start at 2 minutes past 6, which is approximately another minute from now. Okay, good evening, everybody, and welcome to this talk on Exovent. My name is John Pollard. I have just stood down as the regional chair for the Merseyside and North Wales region. And it's a pleasure to welcome you all here this evening, and particularly to a good friend of ours, Ian Jolesbury. Now, before I hand over to Ian for the talk, I just want to explain that at the bottom of your screen, at the right-hand side of your screen, you will see a chat box. So Ian is willing to take questions at the end of your talk. At the end of his talk. So what I'd like you to do, if you have questions, can you please put them into the chat box? And at the end of the talk, once Ian has finished, I will then ask him the questions. So on the question, if you could put your name so that we know who the question is from, and if you can type the question reasonably concisely into the chat box, then I'll ask Ian the question. So very much looking forward to this talk, and without further ado, I'd like to hand over to Ian.
Thank you, John, and thanks for the introduction there. Welcome everyone to Exovent the Journey, rapid engineering in a pandemic versus a highly regulated environment. As John has said, my name's Ian Jolesbury, and you can see from this slide that I don't have a large history in medical devices. In fact, I've got 30 years in aerospace, but nothing in medical devices until I started to work with Exovent at the beginning of 2020. So here's the agenda that we're going to work through. It tries to both explain the technology but also walk you through the journey. So we're going to talk about what is Exovent, what is negative pressure breathing support, and what problem are we trying to solve with it. We're also going to cover what the Exovent solution is, and then talk about the different phases of the activity, the initial startup, the early development in the first 8 weeks, then at that point the recognition of the scale of the task ahead of us, then talking about the support from Portsmouth Aviation, prospects for the future, all the international activity that we've been doing, which has occurred right from the start, some lessons learned, and a brief introduction to the trustees, and then some questions. So hopefully that covers the things that you'd like us to talk about. So who are Exovent? Well, it all began at the beginning of COVID when a civil engineer, Dave McEwen, wanted to be sure that he could look after his family if things went badly wrong. Exovent is now a diverse group of engineers, scientists, and importantly, medics, along with many other people that bring something to the team. In the medics, we have critical care specialists, surgeons, anaesthetists, nurses and GPs, amongst many other roles, and it's the combination of their capability and the engineering capability that makes Exovent what it is. We are not a company that is trying to make the devices ourselves. We are working through other people. We've worked together now for over 2 years on a remote basis. In fact, many members of the team have not met face to face, as some of them are all over the world. It's important to note that Exovent is a volunteer organisation. No one's paid, and we formed the charity in June 2020. And thanks to the Charities Commission, it was approved in record time. So what is negative pressure breathing support? I've got a short video here that explains the mechanics of it. Look closely at the chest as we do this, and I'm hoping that the voiceover on the video is going to work. If not, I'll after a few seconds I'll jump in and I'll give you the voiceover myself.
In negative pressure ventilation mode, Exovent will assist the
So it
patient's
doesn't look
breathing.
like the voiceover is working on this. So what I'd like to do is just talk over it then.
A pressure reduction to the
what
chest.
this is showing is how Exovent
When the
works.
pressure on the chest
You
is
have an
reduced,
enclosure
it causes the
around the
patient to
chest
breathe in.
with a seal at the neck
When
and
the
the hips.
pressure on the chest returns
And
to the
by
initial level,
reducing the pressure in
forces
that
the patient
enclosure,
to breathe out.
you can expand the chest. By cycling that, you can actually drive breathing for someone in that enclosure. There's another way of that operating as well, is you can put continuous negative pressure on the enclosure, and what that does is it expands the chest, opens up the lungs, and makes it easier for someone to breathe, and increases the volume of air in their lungs. And I guess to imagine how it might work, if you imagine how you blow up a balloon, and the first part of blowing up a balloon is always the most difficult. Once it's partially inflated, the effort of inflating it the rest is a lot less. So hopefully that helps. It's a natural approach to breathing, as it simulates the way the body breathes itself, with the movement of the diaphragm down and the ribs lifting up. That creates a negative pressure for the lungs to expand into. As I said, it can also be used as continuous negative pressure, and the combination of those two capabilities gives it a lot of flexibility. So I guess it's a fair question to say, what problem are we trying to solve here, since there's obviously lots of ventilators out there. The obvious answer is, initially it was COVID, and it obviously started with COVID and the shortage of ventilators, but it quickly became clear that respiratory disease was a major problem outside of COVID, and many people around the world do not have adequate access to treatment. Over 500,000 people worldwide have a chronic respiratory disease, and pneumonia alone kills 1.5 million people a year. Over half of them are children. If you do the maths, a child dies from pneumonia every 50 seconds. In countries with, in rich countries, then clearly we have access to intensive care capabilities, etc. But in many low and medium income countries, that access is much more limited, and many people don't really have any access to something that will support them in that way. So if I walk you through what might have happened if you went into hospital in the summer of 2020 with COVID, the first thing they would probably do is to put you on oxygen with a face mask or nasal prongs. As the disease progresses, they might move on to CPAP, which is continuous positive airway pressure, a pressurized face mask forcing oxygen into the lungs, and that was extensively used, has been extensively used to treat COVID. Finally, if this was not enough, there would be a need to have a very difficult conversation about being anesthetized and ventilated. where you're unconscious and a tube is inserted into your throat, and the ventilator controls your breathing. At this point, about half of all people being ventilated did not recover. So for those that had to make that decision about going onto a ventilator, it was not an easy thing. And also for those that recovered from it, there was also a risk of lung damage from being on a ventilator for an extended period of time, and many people were on ventilators for weeks and weeks, which certainly is very challenging for them. One of the key things about negative pressure is that it doesn't require the patient to be anesthetized, because you're not trying to pressurize the lungs through the through the throat. You're basically pulling the lungs out using negative pressure around the chest. Therefore, the patient can stay awake, they can talk, they can eat, they can drink, they can tell the doctor how they're feeling, and they can continue to talk and communicate with their loved ones. Oxygen, obviously, because the face is clear, then oxygen can be given separately as needed, either via nasal prongs or via a face mask. And if ultimately the treatment isn't enough, then there's still the opportunity to move them onto a ventilator if it's been unsuccessful. Iron lungs have been around for over a century, and they were used extensively on the polio epidemic of the 1950s. But it was the shortage of iron lungs that drove the development of positive pressure systems. The modern version of Exovent, it's lighter, only covers the torso, and as with the iron lung, it does not need an anaesthetist. So if we think about how this all started, it all began with Dave McEwen writing to the Cabinet Office. Now, they didn't reply, but someone there put his letter on Facebook, and he started being contacted directly by doctors, engineers, and a variety of other people, all interested in helping. Within days, two of the people that had contacted him had built their own system in their garage, fully functioning, using hardboard, wetsuit seals, a vacuum cleaner, and a simple control system. And here's a picture of one of them. It demonstrates how quickly and easily these things could have been put together had the need materialized in the middle of the pandemic. The team communicated through that period through WhatsApp, and we still do. They met multiple times a day. These days we meet once a week, but at the time we met multiple times a day with concurrent activity, looking at different aspects of the system, and building on each other's ideas and taking them further. So it was a very intense time. It was 7 days a week. It was very much driven by the challenge of the time, and say it was all about sharing continuously to try and make sure that we could get as much progress as possible. But meanwhile, we were approached by Warwick Manufacturing Group, who introduced us to Marshall Aerospace, who had offered to work with us and to help develop the prototypes. Within 8 weeks, we basically had a fully functioning prototype that had been evaluated by the team, or in fact by the team on the team, which could have been used in hospitals and produced in large quantities without any component conflicts with other ventilators. In particular, there were the challenge with the positive pressure ventilators. There were some sensors measuring pressure that were in short supply. This system didn't have any conflict with any of the components of any of the positive pressure systems. It's interesting to know that Marshall Aerospace had to rewrite their engineering procedures to allow this concurrent work to proceed at risk. There was a lot of parallel activity, a lot of risk was taken on board while the project was going on and resolved as we went, as opposed to trying to pin down the uncertainties at the beginning and put together a sequential plan that there was high confidence level in. So this was more about, trying, doing, and learning from that, and using that to move as quickly as possible. The Marshall team worked very long hours and weekends, just as the Exovent team were. And what happened was the support from Exovent moved from initially engineering in terms of the conversations to primarily medical. And meanwhile, we started developing relationships with Queen Elizabeth Hospital at King's Lynn, Southampton University Hospital, and University College London Hospital to identify, to broaden the medical inputs and to identify places where we could actually test these systems out, and hopefully the areas that might be some of the first adopters once the system was approved. Despite the success, there were many frustrations. Funding was always a challenge, but also the UK ventilator challenge, which we thought would be perfect for giving us support, only considered positive pressure devices, despite the century of evidence for negative pressure. The regulatory environment was changing, and in parallel, Brexit meant a doubling of the uncertainty, with CE marking being replaced by UK CA. It also became clear that if we wanted to be successful, the time frames were much longer and involved full medical device approval, clinical trials, and achieving ISO 13485. Marshall's had only ever intended to produce the initial prototypes, and so it became clear that we needed some help, and that this wasn't something that a small charity without support would be able to deliver. So just as all this was becoming clear, we were approached by Craig Stretton from Portsmouth Aviation. They'd already developed a clean water system for LMICs and had started working with Southampton University Hospital to develop some basic medical equipment for them. After some discussion, they committed to deploying a full team and to getting the medical device quality standard ISO 13485, which is they already had the aerospace equivalent of that, but has a whole range of things that are very specific to the medical world. We supported that team with medical input and some regulatory support, and the program transitioned really into a full UK and European medical device approval program. Usability studies at Southampton University Hospital fed into the redesign activity, and a full development and approval plan was developed. So where are we going now? So this year we hope to have 2 devices approved, one in the UK and in Europe, and one in Bangladesh. We're very keen to develop an ultra low cost version that can be manufactured locally around the world and be used in places that don't have any access to intensive care facilities. We also see home use devices that can be used by the patient alone, and wearable versions that can help anyone that struggles to get about because of shortness of breath. Things like ARDS, COPD can cause this. But we also think that there are applications outside of the medical world, perhaps in areas such as sport. There's still much to understand. If we look at the last 50 years, there's been an enormous amount of research done on the respiratory system with positive pressure ventilation. I suspect there's at least a decade of research and trials to be carried out on negative pressure ventilation, and to work out the boundaries and what it's most effective to be used on, what it's least effective to be used on, and how what's the range of capabilities of the system. Without that research, we don't know, but we certainly know that we're certainly very confident that in the core areas of supporting improved oxygenation, we are confident that it'll make a big difference. So we've been working with teams around the world to help make negative pressure ventilation a reality. Here are just some of the people that we've been working with, and in particular, the team in Bangladesh has been making great progress. They should have a system approved this year and have already tested 70 volunteers in a clinical trial. So we feel pretty good about that. But also, there are a lot of other people around the world that we've been working with, and many of them have developed prototypes. The challenge, I'd say, is the going from a prototype to something that can be approved in the local environment. So one of the things that I think we will be doing as we move forward is to connect those countries where a prototype's perhaps been, an approved device has been created in one country, and perhaps we can set up clinical trials in other countries to help accelerate the adoption of that activity. I know it's down as international activity, but I've also put down Durham in the UK. We've done 2 university projects. One with a team of all-female team of engineers in Qatar, who developed a prototype and used that as their second-year university project, and also similarly with a team from Durham University who used it as a university project, and again did a lot of really good work in terms of exploring the design and ways in which it could cope with people of different sizes. So back to the Bangladesh system. Here's the Bangladesh system shown on display at the Cooper Hewitt Smithsonian Design Museum in New York. Both Shaash and Exovent are in an accompanying book about innovation during a pandemic, but in this case you see just the enclosure, but the team have developed the complete system with some support from us, but very much largely under their own steam, which has been great to see. There have been many lessons that we've learned from here, and these are just a few. I guess what jumps out first is just amazing what can be achieved quickly. If everything had collapsed when at the beginning of the COVID pandemic, then I think this technology could have been deployed incredibly quickly. Even at the earlier stages where we had the 2 demonstrators developed within people's garages, that was a technology that you couldn't really put in hospitals. But if the NHS had completely collapsed and nobody had any support, then it was the sort of thing that people could have done locally, and it could have made a difference. Very luckily, that's not what happened, and we're all very pleased that is the case. But nevertheless, this technology could have been deployed very, very quickly. Ultimately, all the barriers can be overcome, but without substantial resource, it's not going to be something that can happen quickly. And even after we have an approved device, I suspect it's going to take us quite a long time. It's going to be quite a long journey persuading medics around the world that have used positive pressure ventilation for the last 50 years that negative pressure ventilation is worth exploring. We're pretty confident that it is, and we'll keep plugging away and providing the evidence to demonstrate that's the case. So we think we will make a difference, and for us, that makes it worth doing. So the charity itself, I mentioned it earlier, we have a vision of a world where those with a respiratory disease have access to non-invasive breathing support when they need it. And that's certainly not the case at the moment. It's not even the case that they have access to invasive breathing support when they need it necessarily. And our initial goal really is to see 1 million lives saved by negative pressure ventilation devices. And we certainly think that that's credible. We have a strong board of trustees, strong and diverse board of trustees, but they're only a fraction of the people that are involved in Exovent, and there are many members of the Exovent team have added enormous value in this program. We've used all sorts of skills, from marketing skills, from social media skills, through to some very, very specialist medical skills that we're very, very lucky to have access to. And again, what makes the difference is the team operating as a whole, but we have a firm backdrop with a strong board of trustees. Our society has a habit of reinventing things. I think at the moment we're seeing an awful lot of that going on. We certainly think that the reinvention of what was the iron lung and is negative pressure ventilation is something that can add enormous value. But if we look back, before cars were run on petrol and diesel, they were run on batteries and hydrogen, and that's exactly the sort of technology that we're working to make to make the standard way that vehicles are powered these days. So things do perhaps go around in circles. As Mark Twain puts it, history doesn't repeat itself, but it does rhyme. So with that, do we have any questions, John?
Yes, we do have some questions, Ian, but can I take privilege and ask the first question?
Absolutely.
My wife was an intensive care nurse, so I'm only too well aware of the extremely invasive nature of positive pressure ventilation. You've painted a picture of negative pressure ventilation as having almost fallen out of fashion. I mean, I can see the attractions of this non-invasive mechanism. Why do you think it fell out of fashion?
Yes, so I can answer that fairly easily. It was really in the polio pandemic of the 1950s that there was simply not enough iron lungs around at that time. And if you think about the challenge of creating more, they were big, heavy devices. They were expensive to produce, and they were slow to produce. And that led to, in effect, an equivalent ventilator challenge of the time, which created the positive pressure devices. And from there, the ability to make many of those devices was the thing that kind of drove if you like, drove negative pressure into the background. There are some other factors that are still relevant, though, and I think we still have some challenges and some opportunity in terms of future improvements and developments. The first thing is, just looking at the device, it's a bit scary, and if you're actually in it, it's surprising how comfortable and relaxing it is. When our team members have tried it, most of them, unless we keep asking them questions, actually fall asleep in it and find it incredibly relaxing. But the visually, it's certainly a little bit scary, and I think we can work to improve that. It's not. There are some challenges in terms of you've got to put a seal over someone's head, you've got to put a seal over someone's waist. So it's not without its challenges, but with using modern materials and using modern development processes, we can continue to improve that and make the usability easier and easier, I think, over time. But it was fundamentally an availability issue that meant that iron lungs were replaced with positive pressure devices.
Okay, interesting. Thank you very much for that, Ian. The next question comes from Jan van Egmont. I hope I've pronounced that correctly. And he's a clinical physicist. And I'm just going to read the question out straight. Is Exovent for the low-income country only? To my opinion, problems with positive pressure ventilation will be avoided by negative pressure ventilation, such as Exovent, such as, I'm not going to try, it looks like antistalysis, pneumonia thorax. Sorry, Jan, I'm sure you're laughing. I'm an engineer, not a medical person. These problems are reported with high incidence during COVID. Am I right about this question? That's from Jan van Egmont.
Thank you. And Jan, it's a good question. The reality is the negative pressure ventilation absolutely has some beneficial treatment effects. If you're, I think when we look at positive pressure ventilation, it's best in environments where it's relatively used for relatively short periods of time. And so if someone's having a heart operation or something like that, that's kind of one of the perfect uses for it. But extended use of positive pressure over a long period of time can create a high incidence rate of lung damage and things like a pneumothorax, where in effect damage to the lung, which can cause it to deflate. So we definitely don't see it as only a product for the low and middle income countries, but we do think it is in low and middle income countries. We think it's something that could operate where nothing is operating at the moment. Many of those people don't have access to intensive care capabilities, and because this doesn't need to, you don't need to anesthetize the patient, because the operation of this is very simple, and you could manage a patient with very limited medical support, then we think that this is something that could have very, very broad use. There are a number of other benefits of negative pressure, which includes things like, again, if you think about your ribs enclosing your chest and your heart, when you use positive pressure, you're pressurizing the lungs and they are pushing the ribs out. At the same time, they're putting pressure on the heart. So it's been demonstrated that negative pressure ventilation actually can improve the cardio output by of the order of 25% against positive pressure. So there are lots of opportunities, lots of benefits we feel, but there are also lots of things that we need to explore with proper clinical trials so that we can provide the evidence quantitatively and qualitatively to support all this.
Okay, thank you very much, Ian. The next question comes from Roland Lewis. Roland is one of our committee members. He has a background in medical engineering and specifically in the regulatory area of medical devices. So I'm not surprised that Roland's asked this question. So the question, Ian, is, and I'm just going to read it out straight. Excuse me. What are your thoughts of the medical device regulation process from an aerospace perspective?
Yes, so I mean, I think the lot of similarities between the processes, but there are differences. I would say that there are opportunities in the medical world for innovation that could be very broadly beneficial, that is relatively low risk, that could operate through a fast track type of process. I think anything that's going to fly with passengers in it, then clearly it's a pretty it needs to follow a pretty strict process. And what we saw recently with Boeing and the 737 MAX is an illustration of where that system fails. But there are a lot of overlaps and a lot of similarities between the two systems. The one where I think the medical devices one is interestingly different is the proactive post-evaluation activity that goes on in the medical world, which, in the aerospace world you definitely get anytime there's an incident. There's an investigation, there's an analysis to try and work out what happened. But from what I can understand of the medical device regulations, there's this requirement for a proactive, ongoing evaluation of the performance, and I think that's a very interesting aspect of it. So I would say I'm not an expert in either regulation. I've program managed significant programs in aerospace, and obviously I've been highly involved in Exovent, but I have to admit not to have read all of either of those regulations in reality. But I hope that gives you some. I hope my answer was helpful, or at least thought-provoking.
Okay, thank you, Ian. We still have questions coming in, so we still have time. So can I encourage the people on the talk to put in your questions into the chat. The next question comes from Philip Cohen, who describes himself as a Norco dental mechanical engineer. I almost thought it was narco, but obviously it's not. Norco dental mechanical engineer. Now, it's a very straightforward question, though I suspect the answer isn't very straightforward. It is, what manufacturing processes are used to produce the device?
Right. So there are a number of different elements to the system. So if I take the enclosure, at the moment it's currently a metal forming process with some welding and some adhesive work, etc. If I look to the future, I think that we will be potentially moving towards things like clear plastic moldings. So I suspect we'll move more towards moldings for the enclosure that will allow us to use clear materials such as perspex or similar materials. The seals, I think, are one of the most interesting areas at the moment. They are in effect sort of derivatives of the sorts of materials that we use in sport, such as wetsuits, but it's actually not wetsuit material that we're using, but we are using material that's utilized in sport. But I think, again, there's a whole range of different ways in which those seals could be created and developed with different pros and cons, including inflatable seals and a whole raft of others. So again, combination of sort of various types of molding. The motor itself is an industrial motor, so standard processes. If I think about what we've used in terms of creating the prototypes and getting to this stage, we've used quite a lot of 3D printing for various parts, some of which we've then ended up ultimately using a different manufacturing process to make in the end. But the 3D printing allowed us to rapidly explore whether it worked, get exactly the right shape, and kind of develop the design in real time. Beyond that, the controller itself is fairly standard electronics. So all of the normal electronic manufacturing processes. But I think at the moment we're using a standard box in effect, which is injection molded for the controller. In the future, I think we'll develop again a specifically designed, more tailored box to do that, and that could be made in a number of different ways. So it's, as you say, I could probably carry on for about half an hour with the different elements of the system and how they're put together. And again, I hope that goes some way to answering Philip's question.
Okay, we still have time for some more questions. So we have another question, but we still have time for more. So can I encourage you to put your questions into the chat? The next question, Ian, is from Anil Patel, who is a University College London Hospitals professor. And the question is, you mentioned oxygen. During COVID, oxygen ran low or even ran out in some countries. Would Exovent be helpful in low middle income countries where oxygen supply can be difficult?
Yes, I mean oxygen became difficult even in some of the richer countries, but where the oxygen is important here is that, first of all, oxygen isn't used to drive the system. So if you look at a ventilator, it's oxygen itself, the pressure of the oxygen is used to drive the system. And things like CPAP use very large quantities of oxygen because it's in effect flooding the oxygen into the body. And also ventilators use quite large amounts of oxygen as well because it's using the oxygen to drive the system. Exovent is independent of the oxygen source, so potentially you can use Exovent without any oxygen at all. If you look at the nature of COVID itself, though, it's unlikely that a treatment that improved the breathing but didn't increase the oxygen content would be sufficiently beneficial. So it's, in that application, I definitely see oxygen being administered separately, but the way in which it could be administered there would be using nasal prongs or a normal face mask, which uses far less quantity of oxygen to achieve the same outcome. So I think it absolutely is relevant, and we saw some terrible images around the world of people trying to get hold of oxygen, and had Exovent been available, it would have been able to help to reduce some of the demand on the oxygen. But I think oxygen would always be necessary to properly treat a disease such as COVID.
Okay, excellent. Thank you, Ian. We don't have any more questions on the chat at the moment. So can I encourage, if anybody else would ask a question, or coming back to Jan, Roland, Philip and Anil, who've already asked questions, if you'd like to in any way follow up on the answers that Ian has given, feel free to add your follow-up question in the chat. In the meantime, can I have another one, Ian? You mentioned the use of 3D printing, which sounds really exciting because of the speed with which you can 3D print components. I just wonder, could you imagine an almost personalized Exovent where certain key parts would almost be 3D printed for the patient, which would make it much more comfortable? I'm thinking about Formula One racing cars, where I understand that the seats are actually personal to the driver. Is that a direction you could see this going in?
Yes, absolutely, and that's a really good question, because if you look at the pictures that I've shared so far, they're of an enclosure that seals at the neck and seals at the hip, but clearly a patient inside that can't wander around. If you start to think about tailoring the enclosure to the individual, then potentially you can match the shape of that individual you can tailor the sealing areas perhaps around the neck and the hips, but also around the arms, such that you could achieve the same objective with something that is mobile. And I think there are enormous opportunities as we move forward for something with a mobile capability. With the benefits of improvement in battery technology, and most of us now have got battery-powered electric drills that are incredibly effective, whereas 10, 15 years ago they weren't. That's the sort of technology that can be incorporated into a wearable version, where it's specifically tailored to the individual. And one of the challenges I think that we need to face with that, first of all, there are challenges around the sealing, all of which I'm certain can be overcome. But the other challenge that we need to face with that is that we don't, as we walk and as we breathe, we don't hold our bodies completely rigid. So within that, I think there'd have to be a combination of some flexible elements alongside some very rigid elements, ultimately to get something that was the most comfortable to wear in that environment. But I do see tremendous opportunities for that, and also in that environment, I think there's also opportunities for other sorts of uses. In my mind, if you're improving the oxygen transfer of someone, then you could perhaps consider roles such as firemen that might be going into difficult environments that are expending huge amounts of energy with all the equipment they're carrying, and maybe something like this could actually help improve their oxygen transfer and improve their ability to work hard in those extreme circumstances. So very much having something that's tailored, I think, is a very real direction that in fact we are already doing some work on, but there's much more to do.
It sounds really exciting to me, Ian, that what you could almost look at as a dormant medical technology has suddenly been revised, looked at again using modern methods, modern materials, things like 3D printing, and opening up a whole area of new possibilities. You almost wonder how many other dormant technologies are out there where something similar could happen, don't you?
Yes, and I'm sure there are. And as we mentioned earlier, thinking about hydrogen and battery power, but in the medical world, I'm sure there are things out there that could be revisited that would bring benefit. One of the challenges, I think, is that there is a lot of learned behavior where I see it in engineering all the time. Actually, if I think about when I look about an engineering drawing and I ask the question, why is that specification or why is that tolerance set at that limit? And the number of times I get the answer back, well, it was always set like that. And no one can actually remember why the original limit was set like that. And when you start to do the analysis, you realize, it's often it doesn't need to be anywhere near that to create an effective product. So I suspect there are lots of areas where things that have been used in the past that have been superseded, there are valuable elements of it that could be recreated and brought to bear in the future, not just in the medical world, I'm certain.
Yeah. Excellent. We have some more follow-up questions, Ian. Philip has a follow-up question. Based on your experience, what would you recommend as the best route for getting funding to develop new innovative medical devices?
Yes, so I think, first of all, I'd say it's important to have a number of organizations or a number of bodies involved in it. I mean, there are a number of funding sources, and you can use anything from sort of Innovate UK, which is a broad innovation funding route, through quite a wide range of specific medical related charities that will provide significant funding for an appropriate technology. It's important to get the technology to a point where people recognize that it's credible, that it's usable, and that there's a really clear route from where you are to a fully approved and functioning system. And so one of the things that we've done is we've tried to pull people from universities together. So we're working with UCLH and Queen Elizabeth Hospital, and working with Southampton University Hospital, etc. We've worked with engineering teams such as Portsmouth Aviation and Marshall Aerospace, and we have brought in a wide variety of know-how from a variety of different sources. So I think it's about putting a team together that's got the right balance of skills within that, and then targeting it into an area where there is a perceived need. And again, how you construct the request is really very important, because it's a difficult, long process to go from even a relatively mature concept to a fully approved device, and the funding needs to be quite significant, particularly if you're going to need to do clinical trials, and that those clinical trials need to be independently monitored, etc. That the costs of those sorts of things can become very, very significant. So I think it has to fit on somebody's key areas that they are looking to fund, and you need then a robust team around you. I hope that helps.
Okay, excellent. Thanks, Ian. We have another follow-up question from Roland Lewis. He said, "Thank you for your answer. You mentioned the device world being slow to adopt new technology. How could the device world learn from aerospace?"
Yes, so I think there are two aspects in my mind to this. One is the approval process, and the other one is the actual medical device world itself. I think there are real opportunities to identify some faster routes to approval that have got. If you've got an innovative group that is bringing a new idea to market, but is not an enormously large and powerful corporate organization, the reality is that those groups need support and help to be successful. And so I think there is an opportunity to look at the process and identify where, for lower risk items, the process can be sped up, but also think about how the support systems in the process are aimed at trying to help something be successful in that process. So one of my observations, I guess, of what I see is that in the approval process, the level of independence is such in terms of those people involved in approval, that there is little or no scope for advice and feedback that goes back to help improve either the product itself or the process within which it's being presented. So it's almost like, show us what you want to do, show us the product, and we'll tell you whether it's okay or not. We won't tell you how it could be improved, or it could have a better chance of success. And I think having something built in there that can, whether that's an independent approach or not, I think could help to improve it.
It sounds almost like it's a yes/no, Ian, rather than a dialogue and a working together sort of environment.
It is, and in the aerospace environment, certainly I've experienced there is more dialogue. There is more. We're not happy with it because of these things. Go away and consider these factors, and come back with a better answer, as opposed to and I could be being unfair, but the feedback I've had from the involvement I've had is that it's a bit more, no, that's not appropriate, that won't work, that's not what we want, you need to do something else. Yeah. And when it's well, what would you suggest? The answer is, well, you need to go away and find out. Yeah. And for those big corporations that are used to doing this all the time, that's perfectly fine. Although even they're perhaps not completely helpful. But for small organisations that are trying to push the boundaries on innovation, it's the impression is that that's really unhelpful.
Okay, thanks, Ian. We don't have any more questions on the chat, so I'll just leave it open for another sort of 30 seconds or so to see if any more questions come in. But in the meantime, can I just say a big thank you, Ian, to you for your talk. It's been absolutely excellent, and it's a real eye-opener. I never fail to be amazed by what a small group of dedicated people from a diverse background can actually achieve when there's a real need. And I think it's really, really impressive. So thank you very much, Ian, for your talk. And thank you to everybody who attended it. And thank you for some very, very stimulating questions. So without further ado, just to say a big thank you to you, Ian. Thank you to everybody else. I think we'll give you a virtual round of applause. And look forward to seeing you for a beer sometime, Ian.
Thank you, John. I really appreciate the opportunity to be able to share the journey that we've gone through. It's been nice to actually put this together, because it actually reminds me some of the things that we've actually worked through in the last couple of years. So John, thanks very much for the opportunity, and thanks to the IMechE for hosting it. That's great.